lesson. And we started with morphine. We looked at the structure of morphine. We looked at the 5 rings. It's a pentacyclic molecule. It's a rigid structure whereby the rings cannot really be changed. They are rigid. And also, of course, we discussed the morphine rule. We also looked at the peripheral groups, the groups that are attached to morphine. We looked at the 3-hydroxy. We looked at the 6-hydroxy group. We looked at the double bond at position 7 and 8. And we also mentioned the hydrogen at position 14 and the nitrogen at position 17. Of course, we had also looked at the numbering. And we were able to look at those groups within morphine. And we discussed in detail how you can change those groups and the effect when you change those groups and why the change in those specific positions, certain or specific analgesic effect. We tried to discuss in details, and I think the last question I asked is, in terms of analgesic activity, do we prefer morphine or the analogs? And of course, I do remember most of you did mention the morphine analogs have much, much higher analgesic activity. But of course, the catch is the higher the analgesic activity, the higher the toxicity. But condition that you are treating, if you are talking about severe pain, then more often than not, you will go for the morphine, because you will go for the morphine analogs, because the morphine analogs will have much, much higher activity. So we did mention, I hope you can be able to remember most of those structural differences or structural modifications that you can be able to do to morphine. And always remember, when you increase the analgesic activity or increasing the toxicity, which is addiction, dependence, and even tolerance. So I think that is one of the last. I think that is how far we've gone. And I remember we had also mentioned the nitrogen substituent, but I might just look at 1 or 2 points, might go backwards 1 or 2 points to add, because I usually keep reading, and if I find any point which is of importance, I feel it a bit delayed. It's my responsibility to communicate that information to you. I think I was able to get 1 or 2 points, which, yes, I did. Yes, there's. Remember, we did discuss the stereochemistry of morphine, and we did mention it has a 5R. It has we start, I think we said we have the 5, we have the 6, we have the 9, we have the 13 and the 14. Cairo. But one of the carbons that is very important is carbon number 9. So I say it's important to go back and mention that to you. But carbon number 9, sorry, right. So remember that carbon number 9, the stereochemistry of carbon number 9 is very important. It should use for the laboratory morphine molecule, which has the activity. It should carry the R orientation, and that gives the molecule the liver configuration. If it carries an S, then the molecule will be dextro, and more often than not, that molecule will have validity. It's important for us to note. And we're just saying alpha to the nitrogen, that's position number 9. See whether I can get that. happened now? Let me go down fast. She's returning so many on. Settings. Last time it worked very well to get me the. Oh, I'm sorry, I think I clicked on the wrong button. At least we are back. I was trying to get the point. I clicked on the wrong button. So I was just pointing that the R configuration of carbon 9 in morphine, very, very important, and which is alpha to the nitrogen. So when you look at this as our nitrogen here, this is our nitrogen, that's our nitrogen, then this is carbon 9. This is the carbon 9, it is alpha to the nitrogen. And we are saying it's optimal for mu receptor affinity. Removal of the N-methyl decreases. Those ones we had said quaternization also decreases because you will also decrease the lipid water. This is lipid water partition coefficient. And I think the point I wanted to fact that in all the analogs and even in the derivatives of morphine, let us look at the equivalent position 9. Because when we derivatize a morphine into a smaller molecule, which we are going to see, so in some of them, the numbering will change. So the position 9 will not be position 9. In some of the molecules, it will be position 1. But always look for that position because that position should have the alpha, that position alpha, the R orientation for maximum activity. I think these are the things we had mentioned. What was most important is that point. So we had also talked about annihilation, buprenorphine, we talked about it, and indeed we went, if I am not wrong, up to this slide where we are seeing morphine analogs, better or worse. And what we are saying is that morphine has 3 polar groups. It has a phenol group, it has an alcohol group, and it has an which we have discussed, have either lost the polar alcohol group or have it masked by the alkyl or acyl group. Remember, we talked about heroin, we talked about heroin, or we talked about even heroin, we talked about the codeine, we talked about even removal of the hydroxyl group at position number 7 and so on. So we could increase either the lipid solubility by either acetylation, even by total removal of the hydroxyl group at position number 6. But be reminded, although the hydroxyl group at position 3 is polar, we require it as a free group for maximum activity. So that, therefore, although the hydroxyl group at position 3 will bring in polarity, it is necessary, needs to be there for binding to the receptor. So we asking the analog can lose those groups, they therefore enter the brain more easily and accumulate at the receptor sites in which analgesic activity. So that is something we have mentioned. But do remember, even as we say that, at the back of your minds, remember that we do require the 3-hydroxyl group for now binding. This drug can get into the brain very rapidly, but its affinity for the receptor can be the undoing in it bringing analgesic activity. So we are therefore saying that, of course, the analogs might be better in terms of activity, but the ones which are best are the ones that are prodrugs. High lipid solubility, you get into the brain very fast, you be prodrugs, change to the active moiety, and therefore bind the receptor effectively. And we can't remind ourselves some of those changes as we move on. So we are saying replacing hydroxyl group with a methyl or methylene increases mu receptor affinity. This is a methyl group. This is the one at position number 6. And if you look here, we are saying this is our morphine. It has that polar group this is morphinone. So it has this hydroxymorphinone. It has that because of the double bond there. It has that methyl group there. It has that polar group there, hydroxyl group, and it has that ketone. One of the things you need to note, and that's why we said we do not have a lot of increase in activity when we make this a ketone and retain the double bond, is that when you do that, you can see the ring C of the morphine still retains what we call the boat configuration. The cyclohexene ring can either have a boat configuration or it can have a chair configuration. When it has a boat configuration, you find that this area here, this ketone, is a hydrophilic group. This is a receptor, which is a lipophilic configuration. You find that the hydrophilic area is interacting with the hydrophobic area. That interaction is not good. So that molecule does not have a lot of increase in activity, although you have made it a little bit more lipophilic. Now, when you remove the double bond, you can see now here is our cyclohexane ring. It acquires the chair conformation. This is a chair conformation. I have said when you have the double, it acquires the boat conformation. When it acquires the chair conformation, the hydrophilic group or the polar group is removed from interacting with the hydrophobic area and therefore better binding. It goes to its own area where it can be able to interact much better than falling on the hydrophobic area, because hydrophilic and hydrophobic cannot bond. So therefore, when you make this a boat conformation and a chair conformation, and you make it a chair conformation by removing the double bond, you have removed the double bond, then you find that you improve the binding to the receptor. Now you have here, you have made it a chair. You have also reduced the hydrophilicity. Again, you can see you really push it very far from the hydrophobic group to bind the polar center much, much better. And in itself being a polar center, that interaction, the affinity to the morphine receptor is much, much stronger in this position. And therefore, this compound where you have unsaturation and you have a ketone in place of a hydroxyl group, you have even much higher affinity for the receptor. Again, when you put the methylene group again, drug to bind very firmly to the receptor, and that is found in naumifene, which is also an antagonist, and it will have much better binding to the receptor than morphine itself. So that is just what we are saying here. And we are saying if you replace hydroxyl group with a methyl or methylene, you increase mu receptor affinity again due to better hydrophobic interactions. Example, the naumifene, introduction of additional naumifene, whereby it has a methylene group in place of hydroxyl group. Introduction of additional hydroxyl group at carbon 14. Remember, we did mention this hydroxyl group, which is found in the antagonists. Most of the antagonists do have hydroxyl group there. And that hydroxyl group we did mention for the compounds we call the oxymorphone, oxycodone. We did mention those oxys have much higher activity, and we are saying it is because there is increased immune receptor affinity due to an increased hydrogen binding to an allosteric. Remember, allosteric is that site which is not the exact site where it's an alternative site, not the exact site that molecule binds on. So introduction of that hydroxyl group introduces hydrogen bonding, and therefore the molecule fits better onto the receptor and therefore activity. And then the carbon 7 carbonate olefinic or double bond changes the lipid water partition coefficient and mu receptor affinity that we have mentioned. Saturation gives water partition coefficient, and also ring C goes from boat to chair, that I've already explained. Conformation that changes the 3D position of the carbon 6 hydroxyl group. It improves. It changes it from binding to the hydrophobic area and therefore better binding on the receptor. this gets rid of the unfavorable hydrophilic hydrophobic interactions, then this also increases immune receptor affinity. Saturation plus oxidation of carbon-6 oxygen produces this one we have mentioned, and I've already explained that when you do saturation and you put a ketone, again, you now further remove the ketone from the hydrophobic area and allow it to bind more favorably in the hydrophilic region. So those are a few points I wanted us to note, that indeed those changes that that happen in the morphine make it bind the receptor in a much, much stronger way. And I needed us to know what exactly happens. I think those are the only points that I wanted us to add. And then, because we keep mentioning this receptor, I also wanted us to look at the morphine receptor, so that as we go to the next category of drugs, we will be able to understand how we keep binding of these derivatives on the receptor. So this is our morphine receptor. So this is a receptor down here. That is the receptor, the whole of this line, that is a receptor. And this is our morphine structure. This is a morphine derivative. This is a morphine derivative structure. So you can see you have ring, or the benzene ring, and it will bind a portion. There is a site within the receptor which we call site D. So the benzene ring, which of course carries is ring A, will bind a site within the receptor which we are calling site D. Then from there you have this portion, the hydrophobic portion here. This hydrophobic portion C, which is also a hydrophobic portion C. So you can see that is the other rings, including even part of the piperidine ring, binding another hydrophobic area, which is the site C. Then, of much importance, and that's why we have said that these groups, the drugs must be tertiary. A means is a tertiary nitrogen, which at physiological pH will be protonated, and it will bind to be carrying a positive charge, so it will bind its negative or anionic site within the receptor. So you have an anionic site, you have, of course, this other hydrophobic area, which is brought about by the other rings, and you also have the hydrophobic area, which is specifically brought about by the phenyl ring. And that's why we have said the phenyl ring must be present, or it's isostere, because it requires to interact with this area compared even to these others. So it requires to interact with that area. Then we did mention of those compounds where we talked about annihilation, or where we did talk about position number 7. There was a substituent. Remember, we did talk about buprenorphine. We said it has a substituent. It has a butyl group, substituent butyl group at position number 7. And those drugs seem to be able to bind. Those drugs seem to be able to bind lipophilic area within the morphine site, which is site A. So therefore, this is the site you see them in the notes having an A with closed and opening inverted commas. So that is a site A, and that is why some of the drugs, when we open up morphine and we form other drugs that do not have the same structure, we find, because they have other groups that have been substituted, they are able to use receptor site within the morphine. They might not bind all the receptors, but they are able to bind some of the receptors, and as long as they bind them firmly, the morphine or morphine derivative or analog will still have activity. Like if you look at the morphine drug, which is up to here, it does not bind the A receptor. And that's why we said sometimes you will have drugs that don't completely obey the morphine rule, but because they do have another structural modification, the A center, there will still be as effective or even more effective than morphine. So please understand that is a receptor that we are talking about, which has a D site, it has a C site, it has a B site, which is very important, an ionic site, and of course the other 3 sites are actually hydrophobic. It's important for us to remember, because now you continue referring to that receptor, and you need to remember to know in your mind, when I say the A site, when I say the D site, which site are we talking about? Sorry. So now we are done with the aliphatic hydro. We still have this here in this position in morphine. We had the ether linkage. You can see in this compound, it does not have the ether linkage. If you remember, we did mention that there are several positions you can have substitution. That was one of them. This was another position. That was another position. No, is it not giving me the dot? Let me see. I have to keep learning. So that's one position. Even now it's giving a very small dot. I don't know why. I need to give a big dot so that. Yeah, good. That is one position where we can do structural modification. This was the other position. This is position number 14. We could also do a modification. And this, of course, we have learned we can do modification. But also remember here, we had, within this, we had our ether linkage. And we had also mentioned that you can also remove the ether linkage. And once you remove the ether linkage, we did mention removal of that oxygen, you increase lipid solubility, and therefore you increase activity. I hope you can remember that. So we are saying now the next structural modification is where you remove the ether linkage with increase in activity. But kindly note, here we had the ether linkage. If you remove that ether linkage and your hydroxyl group, you can see this is a hydroxyl group. This oxygen is the oxygen of the ether, is added to position number 4. You can see that is added to position number 4. This is a that was already there in position number 6. Then you find that this drug has much lower analgesic activity than morphine. This is because that new hydroxyl group has added more. The hydroxyl group, which is free, is much more polar than the oxygen, which is in an ether linkage. And therefore, if you do structural modification like this molecule compared to morphine, you can say we are saying it's 0.1 potency of morphine. So form the catechol type ring system reduces analgesic activity. Catechol is where these two hydroxyl group are adjacent to each other and they are attached to a benzene ring. So that will reduce activity. So you will find that in those other analogs of morphine, where you remove the ether linkage, you also do not add that hydroxyl group. So now that next category, whereby you do quite a number of changes, you do not the ether linkage, you remove also the 6 hydroxyl group, you remove the 7H double bond, the resultant molecules are called morphinans. So the next category of morphine analogs are the morphinans. And the morphinans, as you can see, this is the structure of the morphinans, are drugs whereby the eating found in the natural occurring opioids is missing. You have removed it. And as you have removed it, there is increase. 6 hydroxyl group here is missing. Again, increase in analgesic activity. The 3 double bond is missing. Again, slight increase in analgesic activity, and therefore we would expect that the morphinans will bind the receptor better, they will have much higher lipid solubility, and therefore they should have much higher analgesic activity compared to the morphine and morphine. Is presented by the levofano, which is shown below. So please note the numbering of the morphinans is similar to that of the morphine and analogs, because actually the only thing you have removed is at position 4 and 5, and the oxygen was not carrying any number. So again, the numbering, as you can see, 4, 5, 6, 7, 8. Then we go to position 9, which is attached to nitrogen. I say that's how you always 10, 11, 12, 13, which is our quaternary nitrogen. You can still see that is maintained 14, and then 15 and 16. So we have removed the ether linkage. We have removed the hydroxyl group at position number 6. We have removed the double bond at position number 7, 8, and that is now the morphinan. That is the morphinan. And the first derivative is levofano. And as we have said earlier, remember, introduction of a group improves on the interaction of this molecule with the receptor, improves with the interaction of this molecule with the receptor. So that is doing the same thing. So a free hydroxyl group, they are doing the same thing as we had discussed with morphine and analogs. And of course, even those groups, the way we had discussed them, the same remains. We had said, of course, you can't remove the hydroxyl group, you can't remove the double bond with increase in activity. So indeed, there is no change there. System of the morphinans is the same as for morphine. Compounds are synthetic and are obtained as race mates. You see, when you synthesize compounds, it is very, very hard for you to get a pure isomer. So normally you will synthesize as a mixture of the dextro and levo isomer. And when you get that mixture, that is what you are calling the race mate. The more potent isomer, again, has an R configuration, alpha to the nitrogen. Here, it is 2 carbon, not change this position here. That position here is 2 carbon 9. That numbering has not changed. And we are still saying that this position must carry an R orientation for that drug to have maximum activity. And therefore, the morphinans will also be laboratory for maximum activity. Removal of E-ring increases the lipid water partition coefficient. In general, the morphine responding 4,5 epoxy morphinan. When we say 4,5 epoxy, 4,5 epoxy is just the same as saying 4,5 epoxy is the E-ring. When you say 4,5 epoxy, it is adding the E-rings. And then because we have already given the ring E, we have given it a name, then we can call them derivatives of morphinan. So 4,5 epoxy morphinan is actually morphine and analogs. 4,5 epoxy morphinans are morphines and analog. It's all you have done E as 4,5 epoxy. And then since already you have given that ring a name, you will now call them derivatives of morphinan. The ether bridge does not interact with the receptor, and therefore its removal does not affect mu receptor affinity. For example, the morphinans, which we have seen, the laboratory isomer with R configuration, alpha to the nitrogen is known as levofano. We've already seen the structure. Of course, the other one is the morphinan. Levofano is now when we put a hydroxyl group at position, the interaction of levofano with the receptor. It has a higher analgesic activity than morphine. I have explained it is also a potent antitussive. Somehow, just by removing of that, it also has antitussive activity. But because of its high analgesic activity, you mean also high abuse potential. So definitely, you can never dare use it as an antitussive. It has high activity due to high lipid water partition. Drug with high lipid water or high lipophilicity, it will penetrate the membranes in the brain much, much faster. Very high level of distribution, high concentrations in the brain, they have good activity. Loss of the either oxygen and carbon 6 hydroxyl group, again, that increases its lipid solubility, making it increase its lipid solubility, again, also increasing the lipid water partition coefficient. Higher receptor. These drugs, of course, just by removal of that ring, and of course removal of the other groups we have talked about, you change their affinity. They form the conformation, or they form the conformation that is better bound on the receptor compared to morphine. So what we are saying that the ring E is really not necessary for activity. You can remove it and also do a bit of. It is you are removing it and still do a slight structural modification to the resultant morphinan, to the resultant derivative to get the morphinan, and of course you will have much higher activity. Advantages of a morphine include better oral bioavailability. Why better oral bioavailability? Higher lipid solubility, higher penetration of the BBB. You get very higher concentrations even at low doses. Longer duration of action. You have removed the hydroxyl group at position number 6. There will be no glucuronic conjugation at position number 6, and therefore a slower rate of metabolism. And also compounds which have higher rate of lipid water solubility, they take a longer time to undergo metabolism. So you have also removed the hydroxyl group at position number 6. So no glucuronic conjugation, and generally, drugs with high lipid water partition coefficient also require longer duration to acquire the water solubility that requires them to be removed from the body. What would be the disadvantages? We've already said higher analgesic activity, higher toxicity, especially dependence, addiction dependence, and tolerance. So again, these are not drugs that you can use as antitussives, or you can use over the counter because very high toxicity liabilities. Now, we did mention we talked about codeine. Remember, we did talk about codeine, and when you have codeine, we say codeine is where you have a methoxy group at position number 3. That methoxy group reduces activity. What also was found with the morphinans is that you can also change the stereochemistry. If you change the stereochemistry from levo to the dextro, then you find that the dextro isomer will have minimal analgesic activity. And this we have said, this is the levo isomer that has analgesic activity. So when for the morphinans, you change the dextro, and then you put a methoxy group at position number 3, you will get a very good drug that can be used as an antitussive. And the next time you go out there, when you get an opportunity, I believe you are going to go for your ward rounds. Kindly look for cough syrups. Even when you go to the chemist, cough syrups, and you will see some of the cough syrups will have dextromethorphan. The dextromethorphan has very minimal toxicities because, one, we have said it's a dextro isomer, and the dextro isomer has minimal analgesic activity. Added to that, the hydroxyl group at position number 3 has been changed to the methoxy group, again making it have higher antitussive activity as compared to analgesic activity. So master those changes. They're very important because once you do those changes, then you also change the pharmacological activity of the drug. A drug that had abusive liabilities changes, and of course it can cause a little bit of toxicity, but minimal, and you can actually now use it in a cough syrup as an antitussive. So dextroisomer of morphinan is known as the dextrofan and is devoid of analgesic activity and associated toxicities. As I've already explained, it is a potent antitussive. And because it does not have the associated toxicity, dependence, addiction, abuse, and so on, then it is safe for use as an antitussive. All methylation of dextrofan produces dextromethorphan, which has a higher antitussive activity, as now this is a drug that resembles codeine because you have changed the hydroxyl group, methoxy group. Again, remember, changing hydroxyl group to methoxy group, you also increase the lipid solubility. The drug penetrates the membranes much faster, and it can be able to bind the antitussive receptor is different from the analgesic receptor. So that receptor seems not to require a free hydroxyl group. A methoxy group is good enough. Dextromethorphan is as potent as codeine as an antitussive without respiratory depression and associated effects. And this structure here, you can see it. This so this structure here is what we are calling our dextromethorphan. The dextromethorphan will have the dextro optical activity to be the dextroisomer with the liver, the negative optical activity. And then, of course, at position number 3, it will be a methoxy group. Then here again, we can look at now, this came out a bit small. Oh, again, I can't be able to move this. Oh, yeah, because I wanted to be able to move that, so you have to keep changing these things. So I wanted to make it a little bit bigger so that you can see. So we are saying, if we are talking about levomethorphan, remember levomethorphan is where it's a liver isomer. The dextromethorphan is a dextroisomer. The levomethorphan is the liver isomer. And with, of course, position number 3, having a methoxy group. You can see it's a morphinan. It's a morphinan. It is a morphinan because it does not have that ether linkage, and of course the other changes that we have said. So that levomethorphan, just as we discussed of codeine, will be metabolized by cytochrome P450 enzyme, oxidative and demyelination to give us levofanol. And of course, we did mention levofanol has a lot of abuse potential. So that's why we don't want to give levomethorphan as an antitussive. We want to change it first to dextromethorphan, reduce the analgesic activity, reduce the abuse potential, and then even if it's metabolized, it will be metabolized. It will be metabolized to the dextrofan, and once it's dextrofan, then that will not have abuse potential, and then of course at position number 3 it will have glucuronic conjugation, and once it undergoes conjugation, you know it is highly polar, and once it has very high polarity, the drug will just be removed from the body. So now these are some of the compounds. These are some of the compounds that you can get as the morphinans, and you can see this should be tartrate. It should be tartrate, not tartrate. It should be tartrate, and this is the proper spelling here. It should be tartrate. And when you look at, remember we have always said you can have these drugs either as derivatives of organic acids. If it is a base, remember this is being protonated, so you can have it derivatized into either an organic acid derivative like the tartrate, or an inorganic acid derivative like the hydrochloride. So this is just an organic. So this is the structure of tartrate. It is a derivative of succinic acid. Remember, succinic acid is COH, CH2, CH2, COH. So it's a derivative of succinic acid, where one of the hydrogens in the succinic acid on each of the carbons of the ethyl group has been replaced with a hydroxyl group to give us the tartric acid, tartric acid, and then you can use that tartric acid added to the morphinan. It will give you the tartrate. So you have like the levofanol tartrate. Again, remember for levofanol, then this R will be a hydrogen, and of course, this will be a methyl group. You have butorphanol, and you can see from the name, butor. Butor here means you have a 4-membered ring, and the 4-membered ring is attached here, as you have a CH2 and a cyclobutyl group. And you can see this is the one we are talking about, which is giving it the name, butorphanol. And it has that. Remember, we did mention the changes, which are the structural modification of this drug is very similar to the structure you do for the morphines. And therefore, the minute you start increasing the length of this group and making it cyclic, remember you introduce an antagonist activity, like what we talked about, the naltrexone. So the minute you make that group big, between 3 and 5, then you increase antagonistic activity. Then, of course, we have mentioned the dextromethorphan, where this will be a CH3 group here, and of course, that will be a CH3 group. So those are some of the drugs. Also about them. So the SAR, and we are saying a 3-hydroxyl group, a free, not just a free 3-hydroxyl group is optimal, and a 3-methoxy is less active. Just like the morphine and analogs, the nitrogen substituent produces the same activity as in the morphines. So the group you put there, methyl group, is usually optimal. When you put 2 carbon atoms, still active. When now you go beyond 3, then now 3 and above, you start getting antagonist activity. And I think we mentioned those changes at position number 17. No other substituents may be added to the ring, to ring A, and that is the same thing as with morphine. The C ring must be unsubstituted. Again, the same we discussed with morphine. Position 14 may be substituted. Of course, with morphine, position 6 of ring C is substituted. But with morphinans, C ring is not substituted. There is no unsaturation and no substitution on ring C. Position 14 may be substituted with a beta hydroxyl group with increase in analgesic activity, just as we had mentioned again with morphine, and that is how we got the oxymorphones, the oxycodones, and indeed, if you look at butorphanol, you can see the at position R here, butorphanol is an example with the hydroxyl group. At that position, that increases its binding. Of course, it brings more of the antagonist activity, but it increases its binding affinity to the receptor. So when we draw them out, that is rivalophan. Again, is an OH group, and it resembles it resembles an naloxone, where it has the allyl group. So you can see it has antagonist. It has even higher antagonist activity than nalorphine. Remember, nalorphine is a derivative. It's where you have this group, but in morphine. That's how you get nalorphine. And you can see nalorphine itself is an antagonist, and levalophan has even much higher antagonist activity than nalorphine, and we have explained why, because of those groups, those changes that we have done. It has very weak agonist activity. Then you have cyclophan. My granddaughter. Cyclophan, again, if you look at cyclophan, again resembling naltrexone, where again now you have the cyclopropyl ring, and you can see again it's a narcotic antagonist. So the SAR very similar to the SAR of morphine and the other analogs. It's strong agonist that has been found to be hallucinogenic. Remember, it still has those groups that endear it to bind the agonist receptor more strongly, but it also has antagonist activity. Antagonist activity, remember, it is because of this group here. It is because of that group there. So it has, but cyclophan was found to have hallucinogenic activity, so definitely it's not in. And this is the one we have said has also stronger agonist than morphine, but also has antagonistic activity. Again, you can see this the group you're saying we have there. And remember, you said the lower the number of the atoms here, as long as they are between 3 and 5, when they are 3, as you increase them from 3 to 4 to 5, then you decrease the antagonist activity. I repeat again, between 3 and 5, 3 to 5, you decrease the antagonist effect, and therefore you will increase the agonist effect, slight agonist effect. So that's why we are saying when you look at butorphanol, it is a stronger agonist compared to, it's a weak antagonist compared to cyclophan, because you can see it has 5. Actually, it has 5 atoms, carbon atoms there. We have added 4 because even morphine, all the others, we are not that carbon, because this carbon is part of all the other substituents. So we are looking at that group here. So the group we have added there, we have added an extra 4 carbon atoms, and as you add that group there, the higher the group, the number of carbon atoms, the weaker the antagonist activity. You can see these are cyclo 3 carbon atoms, so it will have much higher antagonist activity. The allyl group is known to be highest. Allyl group is known to have the highest, very high, allyl group known to have very high, also very high antagonist activity, and you can see the number of carbon atoms is in total 3 carbon atoms. So we are therefore saying, if you look at levalofan, please note, it is a morphinan where an aryl group. It's an aryl group. This group is an aryl group. It has a double bond, CH2, CH2. It's an aryl group, just like in the pure antagonists. And this one we are saying, in terms of receptor affinity, levalofan has higher receptor affinity than nalorphine, which has butorphanol, because we are saying this allyl group seems to give much higher binding affinity. So I think the ones, let's not include the ones we can compare is levalofan and nalorphine, because they're the ones, because they're the ones which have the same structure. Let us leave that. But we are saying levalofan will have much higher affinity than nalorphine because of the structural differences, the basic structural differences, and levalofan. And you can see, as I said, you can see this is a chair conformer. The minute you remove the double bond, you get the chair conformer. When in nalorphine, as I said, nalorphine is a derivative, an allyl derivative of morphine. You still have the boat conformer, and you have the hydroxyl group, whereby the boat conformer gives us this hydroxyl group is trying to bind to the site, and they have very poor binding as compared to the levalofan, whereby you have removed that, and therefore the hydrophobic portion is interacting favorably with the hydrophobic portion. And you have, as I have said, the chair conformer and the boat conformer there. The chair conformer gives you the better overall conformation or overall shape of the morphine, of the levalofan shape, to bind the and therefore give you better activity. We've already discussed butorphanol, of course, also, and look at this. It also has the chair conformation because of the fact that you do not have the double bond, again giving it better binding to the hydrophobic center. It has a hydroxyl group, and I believe we are adding the hydroxyl group because of the fact that here you have increased the size to compensate for the loss of affinity, because this group here is slightly. Butorphanol, it has a higher mu receptor affinity compared to morphine. That one we've already discussed. This is due to the 14 hydroxyl group, and with the following advantages: it has lesser or little dependence liability, it has limited respiratory depression. It is a mixed agonist antagonist. So I believe we did mention also buprenorphine, said it's a mixed agonist antagonist, or even a partial agonist, and we are saying it's a mixed agonist antagonist. Remember, antagonist, they'll bind different receptors. They bind the kappa, they'll bind the mu, and have differences in their pharmacological activity. So it's a K agonist and a mu antagonist. Kindly understand, K agonists do not have as high agonist activity like the mu agonist, and then the mu agonist. When a drug binds a mu receptor, it can give you optimal agonist activity to binding the kappa or K agonist, susceptible to significant fast-pass metabolism, and it is administered parenterally or intranasally. It does have the hydroxyl group at position number 14. It has a hydroxyl group at position number 3, so it can undergo fast-pass metabolism. Kappa agonists have lower ceiling and analgesic effects and are not as effective as mu agonists in severe pain. So, like this, we are saying it binds as an agonist and binds the mu as an antagonist, but it still has higher, it's good to understand, it has a higher mu receptor affinity compared to morphine. And because of the fact that it has higher mu receptor affinity than morphine, of course, it is binding the mu receptors for antagonist activity, not for agonist activity. So you can see the change receptors. When it binds a mu receptor, it binds a mu receptor as an antagonist. It binds a K receptor as an agonist. Metabolism of levomethofan there, and we had already mentioned that levomethofan undergo oxidative O demethylation to give us levofano, and of course levofano having very good binding affinity for the mu receptors to give us a lot of toxicity. So I think that, unless there is a question, that finishes our. I don't know whether they had any other notes. So that brings us to the end of the morphinans. Please remember examples. Remember the ISAR. Which groups do you remember? Do you remove? Why do you remove the groups? What is the influence of the change of the conformation of the C ring from both to chair? In naturally occurring morphine, it has a chair conformation. Once you change the double bond, or you saturate the double bond, you give it the chair conformation, which allows that molecule to interact with the receptor in a much better manner. Any questions?
Hello, I have a question.
Yes.
Kindly pardon the difference between bot and chair conformers.
Chair and did you do stereochemistry when you're doing organic chemistry? Yeah?
Yes.
Have you at any one time discussed the molecule called atropine? Anywhere? Yes or no? You have never discussed atropine, have you? Anyway, let me then discuss the chair, and let me get there again. Sometimes it gets lost. Wow, okay. It is obvious when you look at the structure. Those conformers are actually named according to their shape. This kind of is looked as if it's a chair. You're coming like this, you're like this, and like this. You sit like that, and then like that. So the chair, the way you sit, the way you come like this, like a chair, it's like an L, but so this is a chair where you come, and of course it has a support here. This is what touches the ground, this area here. So you sit, if you are sitting, you sit here. That's what we are calling a chair. It's just the shape. It has a shape of a chair. And that's what I was trying to draw, that if you look at it, this is just what we are calling the chair. you consider that you are coming, the whole of this is the here, the whole of this is like now the up. And then this section here is going like this. And then this section is what is kind of supporting your chair. So it is just this shape here, which they look at and they say that chair, that shape, this shape of the cyclohexane ring resembles a chair. So this shape here, but this one here is what they are saying. Is we are saying resembles a chair. Then when you have a double bond or you have unsaturation, this shape here is a boat shape here. Just the shape. A boat looks like that. So that is a boat. It's just the normal boat, B-O-A-T. This is a normal chair, C-H-A-I-R. So they let us understand the conformation whether chair or boat is just from the shape. I hope that point is understood. Then now, if you have the chair conformation, it influences the way the groups, the closeness of these groups, of the groups that are attached to the hydrophobic center. Remember, we mentioned when we looked at the morphine receptor, we said we have the A, we have the B, and we have, I think, even the C. B and C were both. There was A, B, there was D, there was D, and then there was C. D and C were both hydrophobic areas, and then DCP was the anionic center, and then there was A at the extreme end, which was also another hydrophobic center. So what we are saying is that once you, depending on the shape of this cyclohexane ring, this is ring A, that's ring B, this ring C, this ring C. Depending on the shape of this ring C, it will interfere with the way this ring and its, if it has a substituent, binds to the hydrophobic area. The hydrophobic area is D and C. Within, or the hydrophobic site is D and C within the morphine receptor, and we looked at the morphine receptor. So once you have this shape here, if you have a substituent here, it kind of pushes it off from the DC hydrophobic site of the morphine molecule. When it pushes it off the D and C hydrophobic area of the morphine molecule, it is placed in an area where it can interact with the receptor better. When you have the boat conformer, and I've said the boat is just a shape, you can see it actually then orients the hydroxyl group such that the hydroxyl group falls on the hydrophobic site within the morphine receptor. Once it falls, the hydroxyl group is a hydrophilic area. When a hydrophilic area within the molecule falls on the hydrophobic receptor within the morphine receptor, hydrophilic and hydrophobic is like water and oil. They cannot interact. So the interaction of that molecule at the hydrophobic center is interfered with. And that's what we are saying. That interaction is poor when you have a hydroxyl group at that position. The interaction of the morphine, the hydrophobic area of the morphine is interfered with, and therefore poor binding. So let us understand that removal of this double bond and removal of that double bond and removal of that hydroxyl group gives you a molecule that one has a better shape, which is a chair conformer, and of course, again, without the hydroxyl group interfering or falling within the hydrophobic area of the morphine site, and therefore better interaction. That's all we are. I hope that has made it much clearer. Is that better?
Yes, thank you.
Yeah, thank you. If you don't understand, again, you're right to keep asking.